Okay, welcome to lecture 17. Let's go ahead and dive right in, how about we? So, iron 3 hydroxide has a KSP of 2.79 times 10 to the negative 39th. So what is the pH of a saturated solution of iron 3 hydroxide? Well, let's do our ice table real quick. Iron hydroxide, solid, it goes to iron 3 plus and 3 OH minus. Iron hydroxide itself doesn't show up on our equilibrium expression. And we start with 0 iron and 10 to the negative 7th hydroxide because, a neutral solution. Plus X for iron plus 3X for hydroxide because there are 3 of them, which gets us an equilibrium expression of X and 10 to the negative 7th plus 3X. Already, we're looking at a fairly complicated problem because this is an example of what's known as the common ion effect. That makes things difficult. So let's go ahead and leave this problem for a moment, move forward until we come to the common ion effect in our slides, why don't we? And first up in our slides, this should be nothing new for you. Q and KSP can be compared just like any other equilibrium constant and reaction quotient. Okay? So if Q is less than KSP, you're looking at an unsaturated solution. Okay? You could throw more solid in there, it would still dissolve. If Q equals KSP, then you're looking at a saturated solution. You've got as much of the solid dissolved in there as you can get. And if Q is greater than KSP, what you're looking at is a supersaturated solution. That is possible. It can be very difficult to do. Some salts are easier to supersaturate than others. What that means is that the slightest disturbance will cause salt to precipitate right out of solution. It can be very dramatic. It can look really, really cool. But like I said, it's typically fairly difficult to get that to happen. So I'm not going to be showing you any examples of that, but you can Google it. You can Google it if you want it. And now we come to the common ion effect. We've already seen this in weak acids and bases with pH changes and H plus and OH minus. If you mix an acid and a base, you're basically playing around with the common ion effect because thanks to the mediating effect of water, H plus and OH minus have a sort of common ion effect through water. That means that acids and bases have a common ion effect through water. And the common ion effect just looks at the exact same sort of principle, but for ions other than hydronium and hydroxide. So let's go ahead and finish our iron 3 hydroxide example, and then we'll look at what happens when you mix a soluble salt and an insoluble salt, silver chloride and sodium chloride. So here, once again, we have our ice table for iron 3 hydroxide. Now, the question we want to ask is this 10 to the negative 7th negligible? Are we going to be able to drop it out? Because doing that would make the algebra a heck of a lot easier. Solving quadratic equations is bad enough. Cubic equations are possible, but very, very difficult. Quartic equations, x to the 4th and so on, that's kind of breaking brains. So is 10 to the negative 7th negligible? Well, just looking at this problem, I can't really tell. We're going to actually have to work out the equilibrium expression and figure out what's what. And KSP is equal to iron 3 plus raised to the 1st power times hydroxide raised to the 3rd power. Now let's go ahead and just assume that 10 to the 7th is negligible to give us a nice, simple equilibrium expression. And if that gets us a weird answer, then so be it. That will tell us we were wrong, and that means we'll have to do difficult math. So KSP is equal to x times 3x raised to the 3rd, or x times 27x cubed, or 27x to the 4th. So if you'll forgive me a little bit of a shortcut, just eliminate some of the algebra, x is equal to 2.79 times 10 to the negative 39th divided by 27, all raised to the 1/4 power. Or x equals 1.01 times 10 to the negative 10th. So 3x is equal to 3.03 times 10 to the negative 10th. Now let's go ahead and look back over at our ice table to see how things worked out. And what we see is that we're entirely backwards. It's not that the 10 to the negative 7th is negligible. It's that 3x is negligible. Okay, that is 1/1000th, or 3/1000ths of 10 to the negative 7th. It just doesn't show up. This is what's known as the leveling effect of water. For some weak acids or weak bases, water can be a stronger acid or base. And even a saturated solution of iron hydroxide isn't going to change the pH of water. So we're looking at a pH of 7, regardless. So a more interesting question is, what is the concentration of iron in a saturated solution of iron 3 hydroxide? And that actually turns out to be a slightly easier question to answer. Because, if you let me clear up a little room here, now KSP is equal to X times 10 to the negative 7th, raised to the third power. The pH isn't changing, so it's just, a constant. So KSP is equal to X times 10 to the negative 21st, or X is equal to 2.79 times 10 to the negative 39th divided by 10 to the negative 21st. So X is just 2.79 times 10 to the negative 18th molar. So that right there is the concentration of iron 3 plus in a saturated solution of iron 3 hydroxide. The pH doesn't really change. All the hydroxide coming out of that ion is just, the water sort of yawns and swallows it up in its own autoionization expression. And that's why we consider iron 3 hydroxide to be insoluble, because 2.79 times 10 to the negative 18th is a ridiculously tiny number. It is very, very difficult to measure concentrations that are that small. We're talking about a few 100,000 ions floating around in solution. Remember, 1 mole is 6.022 times 10 to the negative 23rd particles. So 2.79 times 10 to the negative 18th. That's 5 decimal places different than that. So actually, a few 100,000 ions of iron. So a very, very small number, relatively speaking. All right. So now let's go ahead and look at our silver chloride solution with sodium chloride. So we hop back to the previous slide, and we see the problem is, what happens if you add sodium chloride to a saturated solution of silver chloride? Well, a silver chloride equilibrium is just silver chloride goes to silver plus chloride. And if you throw more chloride in there, well, that's an easy problem. It's too easy for you guys. You guys should know the answer to this. You throw chloride in there, you're adding product, the equilibrium is going to shift to the left. Way too simple. So instead, let's ask, what is the concentration of silver in a 1 molar solution of sodium chloride? Now, to answer that, you're going to need the KSP of silver chloride, and that is 1.77 times 10 to the negative 10th. So now we go ahead and draw out our ice table. Silver chloride is not going to show up in there. And our initial concentrations are 0 for silver and 1 molar for chloride, because that's coming right out of the silver chloride. And as we've seen, sodium chloride has a saturation of 6.14 molar. There's no way it's not fully dissolved. All right. So our change in concentration is going to be plus X and plus X, giving us equilibrium concentrations of X for silver and 1.0 plus X for chloride. But we can go ahead and eliminate that X. And that is going to be negligible, I guarantee. Okay? There's no way silver chloride is going to dissolve enough in solution to get anywhere close to 1 molar. So KSP is equal to those equilibrium constants, or equilibrium concentrations, X times 1.0 is equal to 1.77 times 10 to the negative 10th. So X is just 1.77 times 10 to the negative 10th molar. Okay? That is the equilibrium concentration of silver in a 1 molar solution of sodium chloride. Just to compare, without sodium chloride, the equilibrium concentration of saturated silver chloride. The silver is 1.33 times 10 to the negative fifth molar. So the other prediction was right. The concentration of silver goes way, way down if you add sodium chloride to a saturated solution of silver chloride. Okay, 1.33 times 10 to the negative fifth is a lot larger than 1.77 times 10 to the negative 10th. Okay, we added a bunch of zeros in there. Okay, it went down by a factor of 10,000, or sorry, 100,000. So it made a big difference. Now that's the great thing about common ion effects. Unless I'm feeling mean, you usually end up with one of your ions becoming a constant. Okay? So the chloride in this case, it didn't change. Okay? The sodium chloride just sort of wiped it out. It made it a constant. And it makes your algebra a heck of a lot simpler. You get rid of a lot of X when you're looking at common ion expressions. It's just a matter of figuring out how to set up the ice table to make it a simple problem. Okay, our final topic of discussion here is going to be coordinate covalent bonding, or a return to Lewis acids and bases. This is basically metals at the center of very often complex ions. It's an interesting field of study that is pretty big in medicine and biology, and also in some materials chemistry. But you guys, for the most part, aren't interested in the materials chemistry the way I was. Okay, so just a quick reminder. In this coordinate covalent bonding, okay, you have a Lewis acid and a Lewis base, such as ammonia and boron trifluoride. So ammonia is your Lewis base. It donates a pair of electrons to boron trifluoride, which is your Lewis acid. It accepts them. And that gets you this big old compound here on the right, the ammonia-boron trifluoride complex. And the bond in between the nitrogen and the boron is known as a coordinate covalent bond. Okay? In a normal covalent bond, each atom contributes one electron to the shared pair. For a coordinate covalent bond, both electrons come from one atom. Okay? In this case, they both come from the nitrogen. Okay? So that's the difference. And you get coordinate covalent bonds all over the place for Lewis acids and bases. So for these metals, we have another example on tap. So down here we have a copper 2+ ion combining with 4 chloride ions to form a complex ion, CuCl4 2-. I want to go ahead and distinguish this real quick from polyatomic ions, okay, like phosphate or carbonate or something like that. Those are molecules that are also ions. Okay? So the phosphorus and the oxygen in phosphate are held together with covalent bonds. Okay? So a polyatomic ion is a molecule that's an ion. A complex ion is an ion made of ions. Okay? So instead of being held together by covalent bonds, it's held together by coordinate covalent bonds. So you look over here on the right, you have copper surrounded by chloride. Okay? Then each of those chlorides has donated a pair of electrons into an empty orbital around the copper, making a coordinate covalent bond. And the overall charge is, the 4- of the chloride plus the 2+ from the copper for an overall charge of 2-. You can get these complex ions with different things, or with strange things, or apparently strange things. For example, you can combine nickel 2+ with carbon monoxide. This was the subject of a difficult math problem I had to do in grad school, so I will never forget it. Each of the carbon monoxides can coordinate with the nickel ion, and you'll get a structure sort of like this, with coordinate covalent bonds between the nickel and the carbons, and you get a complex ion that still has an overall charge of 2+. So you're combining the ion, nickel 2 plus, with the not ions, the carbon monoxide. Those are not ions. And you'll still getting a complex ion. So the complex ion isn't necessarily made of ions. I misspoke earlier. It is an ion overall. Only what's holding it together is these coordinate covalent bonds. Now, I know this video is going over 15 minutes, but bear with me. We're so close here. Earlier I said that this stuff was important to biology. Lots and lots of proteins involve what are known as cofactors or coenzymes. These can be almost anything, but they're often metal ions that have to be sort of snapped into place on the protein structure in order to get them to work. For example, you have iron here in the middle of the heme group. That is to say, part of hemoglobin. Okay? These are also important to medicine. They've been doing some work, some experiment with trying to get metals into drugs, or using the metals themselves as drugs. For example, platinum and silver. And in order to get those into the body, they need to be dissolved. They need to be, or dissolvable, soluble. They need to be aqueous. And from my recollection, silver is an antibiotic, and they are currently exploring the use of platinum, coordinated with various things, as a cancer fighting agent. So these things are kind of big deals. Now, like I said, these things need to be dissolved. They need to be soluble if they're going to get into the body. And one way to do that is with coordinate covalent compounds, complex ions. So, for example, this is something you wouldn't want to do to use it as a drug, but you can make silver soluble, even though usually it isn't, by coordinating it with something like ammonia. So silver plus 2 ammonia will enter an equilibrium and make the complex ion silver NH3 1 plus. And because ammonia is perfectly soluble in water, you can just add as much of that as you want to drive the equilibrium as far right as you want to get whatever concentration of this complex ion you want in solution. So it's a really handy way. Although sometimes you have to be, kind of careful. You might recall an earlier experiment we did in lab, where aluminum hydroxide is insoluble, but you can get the complex ion AlOH4 1 minus. The coordinate covalent ion, complex ion of aluminum with 4 hydroxides. So these coordinate covalent compounds are a big field of study, and if you're planning on going into medicine, you might be seeing these in the future. All right, so just to go ahead and tie this back into stuff we've discussed earlier, in this reaction, the silver ion is your Lewis acid, and ammonia is a Lewis base, because ammonia is donating a pair of electrons to the silver in order to make this coordinate covalent compound. And to sort of link it forward to the organic chemistry you might be doing in the future, the silver ion is an electrophile, and your ammonia is a nucleophile. Okay? So that does it for our coordinate covalent compounds. It also does it for this chapter, which means it also does it for Unit 2. So we are done with this video and this unit. I will see you anon.